Hello and welcome to a presentation on LibreSoc on the rather comprehensive way that we're doing testing unit tests in the development of a processor. The background here is that we're really software engineers rather than hardware engineers, and in addition to that, software engineers with Libre training, which is different from open source training. Now, here's our website, so you'll be able to see things. I'm going to do this talk in a little bit different from normal ones, without slides, but instead actually showing you directly the code, because that's what this is about. So you'll be able to see the URLs in the top of the URL bars as we go along. So first, I'd like to give you some, show you some other projects. There's one really good, very simple RISC-V RV32 core called Minerva, which is only around 4,000 lines of Python code. It's written in Namigen. It took two years for the developers to write it. Now, the thing is, there's 2 years, but there's only actually 3 unit tests. One of them was for the cache, one was the divider unit, and the other one was for a multiplier. Now, anyone who does software engineering who looks at this would look at this in surprise, to say the least. It means that the developers basically created this code without doing any testing, any sort of unit testing or anything, and then finally, when it was actually functional, were they able to actually run high-level tests. If they had had any problems with any one of those high-level tests, tracking it down simply by running instructions is really, really difficult. Now, it's not just this processor. Pulpino as well, the Pulp platform, and also the Ariane. I wasn't able to find any unit tests, modular unit tests. I was, however, able to find instruction cache, data cache, and what looks like evidence of a way to access the system via JTAG or some form of debug interface. But again, that's a high-level one. Now, by complete contrast, Anton Blanchard and the team, when they were developing Microwatt, went all out. And the reason why is because Anton was trained as a software engineer who decided to use creating a power instruction set processor as a learning exercise on how to do HDL. And consequently, he had put in a huge number of tests. And this is particularly funny. I love this. All right. Sorry, we had to truncate this directory to 1,000 files. 1,039 entries were omitted from the list. In other words, he's got 2,039 test files in this directory. Now, several hundred of those are random generated binaries by a special program which generates deliberately its fuzzing program. So some of them are legal instructions and some of them are not. So it's quite good way to catch errors of things that are not actually in the specification, and to find out the behavior on a Power 9 system. So it's really good. But also in this directory, you can't see it because it's not in here, there is also some ZIX tests, there's an MMU test, and so on. But more than that, What it's also got, if you have a look down here, core DRAM test bench, core flash test bench, core test bench, count 0 test bench. In other words, what he did was created a count leading 0 module in VHDL, which is quite straightforward really. Some things on hot, right? But then wrote a test module for it to see, to throw some values and see if it was actually producing the right answers. All right. What that means is that when you was then using it in the module, you had confidence that the individual module being used in the execution engine was actually functional and wasn't the source of the errors. Again, a dcache test bench, divider test bench. This is what software engineers do: multiply test bench and so on. PLRU. Right. But then on top of that, they've also got some. I don't exactly know where it is, to be honest. But they've got a continuous integration thing. So all of these tests are run automatically. So if they make any one commit and it breaks things, they get a warning automatically from the system. But I particularly wanted to show you this one. This is the Dmi interface. This is micro debug memory interface, where they've defined control registers to stop the core, reset, to reset the iCache, to start the core, but also when it's in stopped, they can single step it as well. It says when it is stopping, so you can read the DMI register on that. You can read the program counter, the MSR. You can say which GPR you want to read, and you can read it from there. What I also did was in a patched version of this was I added ability to read the status register and the XER as well, the condition register, etc. And I'll explain why I did that later. So let's now move on to what we did in LibreZog. And it may surprise you to know that the very first thing that we did was to create a simulator in Python, not the hardware. And we did it not by going and reading the spec and implementing the instructions manually. We actually went through, and it took 2 days to extract, we went through the v3.0b specification and extracted the pseudocode from every single instruction. Now I'm deliberately going to edit this so you can see what and we put it into Markdown. And then included comments in the thing of where it comes from. And you'll see this in the v3.0b spec, RA is the destination is RS ANDed with the UI immediate field extended by to 64-bit. And so on. All right. Then we wrote a compiler, which turned that into executable Python code. Now, the reason for doing that is so that we could have a co-simulation of our hardware, a side-by-side single-step thing. But of course, but the problem is that we're writing a simulator, but we don't know if the simulator is correct. So to fix that, what we did was we worked out how to single step QEMU via a Python, it's machine GDBMI, GDB machine interface. And to extract the register file and some of the memory after executing each instruction. All right. And here you can see we can get the program counter and the MSR, link register, and so on. All right. and then did some unit tests on that. So test Hello World Sim. So here's a simple part of the microwatt Hello World thing program, and we ran a test case on that. All right. So then once we had that, um, we were the first thing we did on our in the simulator was in some obvious instructions, like add register 3 to 2, and put it into register 1. We put initialize the registers there, run the program, and then assert. Bear in mind, this is Python, all right? So you use unit tests, all right, and you assert the results. That 0x1234 plus 0x4321 equals 0x5555 in register 1, which is what we expected. All right, etc., etc., and think. Now, in this one file alone, you can see there's 20 or 30, 20 to 30 unit tests. All right, of just different instructions. There's a floating point one as well. Okay. So when we were developing the floating point thing, we'd set up some initial memory, run the LFSX instruction from all registers are 0 by default, and sure enough, we find that the register 42013333, sorry, 42062666 is converted to the 64 bits value 420666. So again, thing, instructions. We're testing individual instructions here, right? And look how many there are, all right, in different categories and features. But that's just of the simulator, okay? All right. So that's slightly different from this one, which is a co-simulation of where the testing run test program will compare QEMU results against the simulator results after every single instruction. It's horribly slow. The Python GDB my interface runs at 1 instruction per second, so we try and avoid it unless it's absolutely necessary. All right. So here you can see establishing the simulator, and then executing one instruction, and afterwards there's a different variation of this. This one actually runs QEMU through to the end, and then does a register compare, and a memory compare, and then prints it out for us, and performs the Python assert here to show us that whether it's which bits succeeded and which bits failed. So it got sufficiently comprehensive in the test, so we actually had to subdivide them down into different categories by the pipeline. Each of these contains 1 or 2 files, each of which will have between like 50 to a couple of hundred unit tests. The div and the multiply one are particularly involved because we had a lot of issues with that. The corner cases, particularly with overflow. In the case of the ALU, you can see we've got EXTSW, SUBF. These were regression tests. We had some issues with those ones. We just leave them in there. If it passes, great. Add, subtract. There's 60 unit tests here. You put it in random values. Add ME, etc., etc. I mean, it's really extensive. This is what you do. If you're doing software engineering. The load store ones, again, you can see we're testing different aspects of load and store. So this is, but by this time we're running the HDL against the simulator. So we've gone from QEMU. We developed the simulator, compared it against QEMU. We then dropped QEMU and you compared the simulator against the HDL, right? Which again was in Python, right? Now, For SVP64, we couldn't actually do comparisons because SVP64 isn't actually in QEMU at all, so we've had to do something slightly differently. All right, but here you can see that what we're doing is we're using the unit tests themselves and the strings as documentation. So anybody who wants to learn about how to do SVP64 create style vectorization can come to this file, these unit test files, and have a look and see what they do. For example, you can see that here that when sv.add with rc equals 1 will produce a vector of condition register files. So yeah, let's skip that one. Now, just like in MicroWAD, we're doing low-level unit tests first of all. Okay, so this is the implementation of pop count. It's quite complex to understand what's going on. We put a comment at the top because software engineers, you put a comment at the top. You know, and you comment the what's going on, right? But it's still quite complex. So we also include formal correctness proofs. Now, here is a very simple version of pop count. A result equals 0. For each bit in the result, add it as like you would an integer, and you end up with a result. Okay, it's not fast. It doesn't have to be. It has to be obvious so you can understand what it's doing. And that's that's the importance of formal correctness proofs. So further down here, where's the pop count thing? Right. What this case does is when the data length equals 8, it does a simple 64-bit pop count, the simple one, and asserts that the output from our module was equal to our simple version. Now, the importance of formal correctness proofs is that they go looking very, very hard for cases which demonstrate the assertions to be false. It's quite interesting. Right, so there's an additional thing we're doing in here as well. All right. Then in addition to that, once we've put that together with the formal thing, we also have the logical cases. Right. So we've got formal correctness proof, and we've got individual unit test unit test cases which are run against the pipeline. All right. So again, you can see we've got well-documented Cray-style vector SVP64 unit tests. In this particular case, it's running a vector of too long, length 2, initializing some of the values of the registers there, and then describing what the expected results are. Now, again, here is the actual pipeline that's being tested for the logical thing. So you can see that the AND operation is there, the OR operation is there. Get a little bit more. That's initializing that pop count module, which we previously tested with the. You're getting the idea. All right. Now we're going up the stack. So we've gone modules, then we've gone the layer up with the pipeline, which uses the modules. All right. Well, we have an additional layer on top of this, which we've called computation unit. Now, this pipeline here is this block here called computation, and there is some gating on both the input and the output. And what we've done is we wrote another unit test which uses those individual tests to run on the computational unit wrapper around the pipeline before it gets linked into the register files. And then finally that gets linked to the register files, and we run all of the unit tests that were previously run only on pipelines again on the actual instruction runner, the actual CPU. Okay, so we test the modules, we test the pipeline, we test the computation units, we test the register files, and then finally we combine the register files with the pipelines, with the instruction decoder, and chuck the exact same unit tests at the whole lot. Unlike, and this is finally, absolutely finally, this is where you get to the top level, which all other systems, open hardware projects I've seen, finally get to, right? Except with the exception of microwatt. Now, if that wasn't enough, I mentioned earlier we'd have this DMI interface, debug memory interface. We've done the exact same thing in Namigen for LibreSoc. And then what we've done, I'm running out of time, I better move on. What we've then done is we compiled both of those CPUs to Verilog and did a single step. I know what I wanted to show you here was here's the actual use of the DMI interface. So we're using the DMI, we're putting the processor into stop mode. We're then setting up the memory and the test memory from the unit test, and then telling the processor to start. Okay, it then starts running, and the simulator executes one as well. And when you get to the end, tell the processor to stop. And then you can extract the condition register, the XER, all of the registers. Again, this is testing the debug memory interface apart from anything. And finally, pull a reset so that before you use the CPU to run the next test. Now, when we did it for the we did things for comparing against microwatt, we wanted to single step those programs, those massive 1,000 programs, on a per instruction basis. And so what we did was use the exact same DMI interface that both processors have, and go through sending requests for the condition register XER, every single GPR, and so on, but displaying them and doing a printout using the Verilog dollar display thing, and then producing a pair of 100,000, million line long files, and just doing a diff on the two. And any time that there was a difference in the files, we found that there was a discrepancy in our code. We knew exactly which instruction it was and could go and fix that instruction. All right. As if that wasn't enough, we then did do the tape out and the layout, and that's a very pretty version of the chip that we've got. And then extracted from, because Coriolis 2 does a subset of VHDL, we were able to extract the VHDL and run it through CocoaDB co-simulation. And here what we've done is we've actually run a unit test which accesses the JTAG interface of the simulated code. And we're able to run JTAG tests running the ID code, running a boundary scan, and there's an additional one which is testing of wishbone memory access, because we want to be able to upload to the memory to the core. So where's the wishbone test? Down here, yeah. So it's over that DMI interface, which has the JTAG wrapper. We're running wishbone commands. But the funny thing is, the hilarious thing is that both those exact same JTAG tests can be run against the FPGA and against the Verilog simulation. Whilst you're running a simulation, we can do JTAG remote debug using OpenOCD. It's very, very funny thing, but it's exactly the same code running against the same things. Simulation, FPGA, CocoaDB simulation, and finally against the ASIC. So Yeah, that's it. That's it. Thank you very much. If you'd ever like to help with this project, here's the instructions. So it's on the LibreSoft.org. You'll be thing. We have sponsorship from NLNet. You'll be able to do this even as a researcher. You'll be able to help us out and get paid. Thank you very much.